Questions. PA2 due tomorrow morning at 8 o'clock. Please do not forget. Alright, well, quick run through on the ODP. So we're building our, let's see, we're supposed to have a free function. Do we put that in the delete function? So for PA2, yeah, you want to free all of your memory that you allocate. So there's two places that you need to do that. One is in the delete function. When you delete a node, last thing you do is free it. But then also when your main program, when the user says X to exit, you need to go through and free any nodes that you still have in the list, including the Sentinel node. So you'll actually be calling free in two different places. So 209, we were removing a middle node from a linked list, and I put in a temporary variable here just to avoid having to do double arrows. So basically you're passed in a node n, that's this first node. I set temp, which is a struct node pointer, equal to the thing that n points to. So temp is my name for this middle node. And then basically set n next to whatever temp next is pointing to. And I did that so that I could call free. If I don't save this middle node in a temporary, once I change n arrow next, then I have no way to get a hold of this node. And if I free this node first, then I can't refer to temp arrow next, because once I free that block of memory, I don't have access to its next field. So I almost inevitably have to use a temporary variable either to hold this node that I'm going to free eventually, or to hold this address that I'm going to change my first node to point to. So just be careful with that. If you're getting Valgrind issues, it could be that you're freeing something too soon, or you're using something from a spot that you freed. So be aware of that. Can we have a main.h? Absolutely. In fact, I recommend it. All right, other questions? Okay. So let's go back to looking at implementing stacks. And we looked at memory yesterday, and we talked a little about how, at the hardware level, a CPU will usually implement a stack, and the stack is just sitting in memory. And there's a thing called a stack pointer, typically a register in the CPU, that points to where the action end of the stack is, what we call the top of the stack. We can mimic that ourselves and implement an array in C that acts like a stack. So So what might this look like? Let's go ahead and make an array. And what are the two main operations we do with a stack? Push and pop, perfect. So what does a push do? A push adds something to the stack. And let's say we want to push a 19. Well, we can just go ahead and we can put that 19 right here. And so if this was a you know, vertical stack, we would be thinking of it like this maybe. And now let's push 105. Now in the physical stacks that we started off with, you know, a stack of plates, for example, if this was what our stack looked like and this was the 19 at the top of the stack, the 19 would move down to here and the 105 would go in its place. But that's inefficient, right? That's going to require us, if we have a bunch of things in the stack, to move everything down one spot to make room for this new thing we're pushing. And we're not going to do that. So instead, what we're going to do is we're going to change our notion of where the top of the stack is. So we're going to push 105. We're going to store it at the next location in the array. And we're going to have this stack pointer, which says, hey, that's the last thing that we pushed. All right. So conventions here. So for push, increment stack pointer, and then save in our array at the location given by the stack pointer. So now if I want to push a 0, 2 steps. First thing, increment the stack pointer. So change the stack pointer to be a 2 instead of a 1, and then save at the location given by the stack pointer, so this is where we push our 0. And we got GNR going in chat, so that's good stuff. All right, so push, very straightforward. Pop is the opposite. So for a pop instruction, so we get the value at the position given by the stack pointer, and then we decrement the stack pointer. So if we call pop, that's going to get the value at the stack pointer, which is a 0, and then decrement the stack pointer. So SP will go back to here. All right, so they just, you know, they complement each other. Push and pop. Pop undoes the effect of a push. And again, you know, even though I pop the 0 off, it's still sitting in memory. Generally, a stack won't touch the things that you popped off. We're just not referring to it anymore. Right? The top of the stack is right here, and if I do another push, so I push a 55, what do? Increment the stack pointer. So change SP to here. And then save our value at the location given by stack pointer. So we're going to save our 55 here. Now that 0's been overwritten. And as I mentioned yesterday, there's different ways we could do this. This is one particular way. When we push, we increment the stack pointer, and then we save. When we pop, we read, and then we decrement. But there's nothing wrong with saying, well, first we're going to save at the location given by the stack pointer, and then increment. And when we pop, first we decrement, and then we read the value. And that just changes the notion of the stack pointer. So with this setup, the stack pointer shows the last thing that was pushed. So anytime that I look at stack pointer, if it's equal to a 2, that's the last thing that was pushed. Which means when I pop, that's the thing I want to return. And then I'm going to decrement the stack pointer. And yeah, this is a really good example where if you have uninitialized variables, lots of weird things can happen. Because your local variables come from the stack, and who knows what's in the stack? It's just, you know, whatever happened to be there. And, you know, depending on your compiler and operating system and so on, there's no reason why, you know, when you have a chunk of stack space being used for local variables, there's no reason you can't have code in the beginning of your program that zeroes that out, for example. But, you know, in terms of efficiency, probably unless the user says, I want this to be set to a 0, let's save time and not bother initializing. And just trust that the coder will initialize things when they need them initialized. Alright, so if I do a few pops, first pop will give me a 55, the next pop will give me a 105, and after I pop off the 105, right, one pop moves my stack pointer here, another one moves my stack pointer here. If I do one more pop, that's going to give me the 19. So I'll get the value at, you know, index 0. And then I'm going to change my stack pointer to be -1. So for us, yeah, pop's usually going to return the value of the thing that it removes. If you've done 270, pick processor's pop instruction does not do that. It just changes the stack pointer. But we're almost always going to think of pop as, you know, get the value at that location, adjust the stack pointer, and then return that value that you got off the stack. So at this point, if I do another pop, I'm going to try to read what's at index -1 in my array, which is not meaningful to us. So that would be a stack underflow. And in our pop code, presumably we would check to see if stack pointer was negative, and if it was, instead of reading the value from the negative part of the array, we would just say, hey, stack underflow. So 2 error conditions possible. Stack underflow, which is an attempt to pop from an empty stack. And stack overflow, which is an attempt to push to a full stack. We're getting into lots of lingo here. All right, overflow we're not going to worry about too much in most cases, but in the case where we're implementing our stack with an array, we do need to worry about overflow. So suppose we set up our stack to use an array of 10 elements. So we could store values, you know, in each of these elements. So what's the overflow condition? We're incrementing the stack pointer before we push. So we would increment the stack pointer to a 9. And we would save some value in that location. So for this particular implementation, we would want to do the following. If we're about to do a push and the stack pointer is already equal to 9, that's an overflow. Because what we're trying to do is increment it to 10 and then store something at element 10, and there is no element 10. If we're about to do a pop, we want to say if stack pointer equals -1, then we have an underflow. So that would be our test in the beginning of a pop call. So pretty straightforward. But again, there's variations we could do on this. So let's look at what the code would actually look like for this. So increment stack pointer equals stack pointer +1, and then save your value that you're pushing onto your stack. So what would my code look like to implement a push using this style of stack? 1 or 2 lines. And let's suppose my array is actually called stack, and my stack pointer is called SP. I'm going to have so much fun when we get back to in-person classes, because I'm going to get a bunch of SpongeBob money and a little cash register, and I'm going to hand out money when people answer questions. And I don't know what you're going to be able to use the money for, but maybe I'll let you use it to buy, like, you know, slip points on due dates or points on quizzes or something like that. But we're going to go to the extreme opposite end of what Zoom feels like sometimes. All right, go ahead and chat. Pop in 2 lines of code for doing a push implementation. That would be awesome. All right, I'll do the push and then I'll let you do the pop. Okay, if SP is not equal to 9, push number. Cool. So our push could be something like stack bracket plus plus SP equals N. Yeah, so N or number or whatever we call it. So this is where we see this is a pre-increment, right? This says take the stack pointer, add 1 to it, that's our increment step, and then use that as an index into stack and save our number n at that location. And if the stack pointer is equal to 9, we do something, halt and catch fire or whatever. Alright, so what about a pop? So if the stack pointer is not negative, what's our corresponding pop instruction look like? What do we want to return? So SP is the stack pointer. That's the index into the stack. Star SP is closer. N, we don't have an N because we're just doing pop, which doesn't take an argument. Ampersand SP would give us the address of the stack pointer, but stack pointer is just a plain old int. But we're getting closer. There we go. So stack bracket SP, that's the value that we want to return from the pop. But we also want to decrement the stack pointer so that the next time we pop we get a different value. So we could, set return value equal to stack bracket SP and then decrement SP and then return that value that we saved. But we could also do it like this. So remember in C, if we do a post decrement, it says use the value of SP and then decrement it. So this would actually be returning stack bracket SP. But before our function exits, it will actually decrement the stack pointer. And this and this, there's some nice harmony there. So pre-increment, post-decrement for push and pop. And again, if the stack pointer is already negative, we have to decide what to do. So return, dead beef or something. All right, yeah, it is early in the morning. I understand that. All right, so this is one implementation. Let me just show you a different possibility. We could implement a push. At the location currently pointed to by stack pointer, and then increment the stack pointer. And our pop could say decrement the stack pointer, and then get the value. So in this case, our stack pointer would be initialized to -1. The first time you push, we increment, in this case our stack pointer is initialized to a 0. The first time we push, we save at that location, increment the stack pointer. Push again, increment the location, save at that location, increment the stack pointer. And now when we want to pop, first thing we do is decrement the stack pointer and then return that value. So in this mindset, what is the SP showing? In this case, the stack pointer was the last thing that was pushed. So here SP shows where the next push will be saved. So top of the stack is moving in this direction. And so this would be stack bracket SP plus plus equals N, and the pop would return stack bracket minus minus SP. So this would decrement the stack pointer and then use that to index the stack. This will index the stack with SP and then increment it. And it's analogous to what we were doing before, except here we were doing a pre-increment on a push, here we're doing a post-increment on a push. Here we were doing a post-decrement on a pop, here we're doing a pre-decrement. So there's symmetry. Symmetry is nice. Your initialization changes. In this case, we want to initialize the stack pointer to -1. Because the first thing that we push, we're going to increment stack pointer and store it right there. In this case, we initialize the stack pointer to 0. In this case, if the stack pointer was 9, we had an overflow when we tried to push something more. In this case, if the stack pointer is 10, that indicates an overflow. And if the stack pointer is 0 and we try to pop, that's an underflow. So the reason for going through these details is, 1, for you to see them, but 2, for you to realize that don't try to memorize this stuff. Right? Because there's multiple versions. There's 2 other ways we can implement this in an array. Don't try to memorize, should this start at 0 or -1? Does it overflow when it's equal to the size of the array or equal to the size -1? Figure it out, right? And each time that you try to implement a stack, if you force yourself to go through and figure out, you know, is it a pre-increment, is it a post-increment, etc., right, you'll understand it better in the end, as opposed to going back to your notes or, heaven forbid, going online and, you know, looking for sample C code to implement stack with an array, because that's just a big rabbit hole you don't want to go down. And it's very simple, right? It's 2 to 3 lines of code to write a push, 2 to 3 lines for a pop, but you want to figure it out, right? Yeah, so this is something you hear in math classes, right? Don't memorize formulas, derive them. And yeah, there's a time issue when you're taking a test, but when you're doing homework, right, definitely spend time, you know, going from what you know to derive what you're trying to understand. Because the goal is not to memorize, right? The goal is not to be able to derive. The goal is to understand. And coming up with this when you're thinking about stacks, that helps you understand it. Alright, the other versions of this that we don't normally see that often, we would simply start the stack at the high end of the array. and move down towards the beginning. The nice thing with doing a stack in this direction is if you get to the point where there's an overflow, you could allocate a bigger array dynamically, copy this stuff over there and say, oh no, my array's not 10, it's actually 100 elements, and now you've got more space to grow. Let's see, quick question for PA2. Do you want the success fail messages like PA1? No, I want them exactly like they are in PA2, and there are some differences. So make sure you go through PA2 and use that as the guide. Cool. All right, so SP is the stack pointer, right? And all stacks have a stack pointer. And whether it indicates, you know, the last place that you pushed or the place you're about to push, that depends on the implementation. And then top of stack is basically the same as stack pointer. And again, it could point to the last thing that was pushed. It could point to the next location you're going to push. But when you hear top of stack, we're really talking about, you know, where the stack pointer is. All right. Questions on that? Yeah, I still want you to implement an out-of-memory option if every time you call malloc, you want to check the return value. And if it returns null, then I want you to do whatever leads to, you know, saying you're out of memory. I'm not going to suck up all the memory on the server to test that, but I will look at your code. All right, so let's look at queues. And with linked lists, implementing a queue was pretty straightforward. It was almost the same as implementing a stack, except we read from a different end of the list. With array implementation, queues are a little trickier. So this will catch you by surprise if you come back to it later. So let's suppose I have an array of 10 elements. I'm just going to call it Q. And remember, with Q, we have two operations. We have insert, and we insert at the head, and we have remove. We remove from the tail. Nope. Insert at the tail, remove from the head. So head of the queue is where we take things out of. Off with their heads. All right, we need a pair of pointers in this case. With a stack, we insert and remove from the same location, so we can have one pointer which says what's the top of the stack. That's where we're going to push, that's where we're going to pop from. With a queue, we've got two of these things. And so we're going to make a pair of pointers, and I'm going to call them head and tail. I'm not going to use arrows. It's just extra stuff to erase. So the tail is T, the head is H. All right, so what does insert do? Well, we're going to insert at the position given by the tail. So we're going to say Q bracket tail equals N. So let's suppose we're inserting a 5. We're going to store that at the position given by the tail. So we're going to write the 5 right here. and then we're going to increment the tail. If I insert an 11, I'm going to store that at the position given by the tail, which is right here. So I'm going to store my 11 here, and then I'm going to increment the tail. Now, if I say remove, if I say remove, I'm going to return the value at the position given by the head. The head is sitting back here at 0, so remove is going to return our 5. And then we're going to increment the head. So head will move up here. So T always shows me where my next insert is going to happen. My next insert will go right here. H shows me where my next remove is going to happen, which is right here. So if I insert a 7, put the 7 where the tail is, increment the tail. And I can keep inserting things and incrementing my tail. And let's say I've gotten to this position right here, where my tail is down here at the last element of the array. And let's say I want to insert one more thing. I'm going to store that at the position given by the tail. I'm going to increment the tail. Well, now my tail is pointing to position 10, and that's a problem. So what should I set the tail equal to? And then we'll deal with the question in chat. The tail was pointing to 9, I just incremented it. We'd like the tail to roll back over. So we actually want to set tail equal to tail plus 1 modulo 10 in this case. So tail comes back here. Is that a problem? No, that's perfectly fine. This spot is still unused. That 5 got removed a long time ago. And if I do another remove, right, I might pull that 11 off and change the head over to here. And now, where is my Q in memory? My Q actually occupies all of this space and this space. So it's a circular Q. It doesn't always start at one spot and end at another. Sometimes it wraps around. In this case, it starts here, that's the head, and then the elements of the Q go back here and down here at the last part. It wraps back around to here. Now, if I insert another element, I'm going to insert at the tail. The tail is right here at the 5. Yeah, I inserted at the 5, but I didn't move it. So the tail is right here. All right, if I were to insert one more thing at this point, I would store it right here. My tail would increment to this spot right here. And at that point, my queue is full. Because, you know, the first thing that I'm going to remove is this 7 right here. That's the head of my queue. This is all part of the body. This is part of the body. This is the tail. But if I add something more at the tail, then every spot in my array is occupied. Alright, so there's one detail here. If our queue is full, in that case, the head and tail would be equal to each other. But if our queue is completely empty, the head and tail are also equal to each other. And so to tell the difference, we would need a separate flag that says, hey, your queue is full. So we usually use a little trick. At this point where tail plus 1 is equal to head, we say the queue is now full. And we're not going to actually let you add one more thing in this location. Even though technically there's a spot in the array that we could store one more thing, that would turn the tail and head to be equal to each other. We're not going to let that happen. So we're going to say if tail plus 1 equals head, then the queue is full. And what we actually want is if tail plus 1 modulo 10 is equal to the head, then the queue is full. Even though it's technically still got one open spot in it, it just kind of simplifies your life to just eat that one spot of space. Because now we can say if tail equals head, then the queue is empty. So we can detect those two situations. So that's a full-blown circular queue implemented in an array with a pair of pointers, one for the head, one for the tail. Insert, remove, check for empty, check for full. And when the queue is empty, you know, the first time that we set this queue up, head and tail are probably sitting right here. But head and tail could, you know, both be sitting right here and we'd have an empty queue. So think about the life and times of the data in this queue as you insert and remove. And, you know, we start off here, we add some things back to here, we remove a few elements, we add a few more elements, we remove a few, we add a few more, which wraps around. We remove a few, we add a few more, we remove a few, which wraps around, we add someone, we remove something. Right, when we've dealt with the last customer, head and tail could both be sitting right here. So our empty condition is just simply head equals tail, as opposed to head and tail are equal to 0. And sometimes it may help to picture your array like this, where this is element 0. And that's really all we're doing with these modulo operators. We're basically making it so that if you go past the end 9, you just come back to the beginning 0. So that's why it's considered a circular queue. I think that's where the terminology comes from. But then like this, it's not as seemingly random to flip around at the end. All right, questions about this? So how do we tell the difference between empty and full again? So let me do a clean version of this. So to insert, we're going to store at the tail. And we're going to increment the tail and wrap it around. So let's suppose our Q is an integer array of size. So that's our insert. Our remove function will be something like this. Return value equals Q bracket head. And then move the head and roll it over. And return the value that we pulled out of the array. To tell if the queue is empty, just see if the head and tail are the same. To see if the queue is full, we ask the question, will inserting one more thing make the head and tail the same? In other words, are we down to where there's a single open spot? So will inserting one more thing make the queue full? So inserting will say add one to the tail. So add one to the tail, roll it over modulo the size of the array, and see if that's equal to the head. So return head equals tail plus 1 modulo size. So there's the difference between empty and full. Empty, they're exactly the same. Full, they will be exactly the same if you were to increment tail. Our initialization function just set the head and tail equal to each other. And it doesn't really matter what value we set them to, as long as they refer to some location in the array. So we could set them to anything between 0 and size minus 1, but you know, 0 is easy. And then the two details in our insert function, before we insert, check to see if our queue is full. And our remove function, before we remove, check to see if the queue is empty. And again, you have to decide how you're going to deal with error conditions. Usually not by printing a message, though. Usually we would set a flag somewhere. And so for insert, right, we can just return a value which says, did we succeed or not? For remove, we might pass, you know, the address of an integer that'll hold a flag telling us if there was an error or not. And then if the queue is empty, we'll set that error flag and say, hey, we didn't remove anything because there was nothing in the queue. Alright, so there's your interface between a calling program and an implementation of a queue using an array. If we implement a queue using a linked list, these would look the same, right, as far as how we would call them, what we would pass, what the behavior would be, but the way that they implement that behavior would be totally different. This would be, you know, inserting something between a sentinel node and the thing it points to. This would be removing the thing the sentinel points to and changing the sentinel to point, etc., etc. Right? But these functions would be the same in terms of how we call them, what we expect the behavior to be. Alright, that's stacks and queues. Maybe we'll write some code in class tomorrow or something. I'll give you some ODPs related to this, probably next week. And we'll go on and we'll start talking about hashes. Cool. Have a good one. I will see you tomorrow.